Hello again. This is Math 2233 coming to you from the College page, and the title of this lecture is The Next Chapters in Your Never-Ending Story. Please be attentive, listeners, as you watch this video. The main results of vector calculus are all higher dimensional versions of the fundamental theorem of calculus. To help you remember this, we collect them here together without detailed hypothesis so that you can more easily see their essential symmetry. There's a fundamental truth going on. Notice that in each case we have an integral of a derivative over a region on the left-hand side. Here, 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 and here. And on the right side, here, 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 and here, involves the value of the original function only on the boundary of the region. You studied this in Calc 1, and in Calculus 3, you studied this one, and this was Green's theorem. And in the Math 2235, you would study Stoke's theorem and the Divergence Theorem. And in addition to studying those theorems, we would invest considerable time talking about the parameterization and orientation of surfaces. So these S's have a little bit different meaning, enhanced meaning than what we have here. The Stokes theorem deals with circulation, and the Divergence theorem deals with the physics quantities of flux. But there is one fundamental message through all of these, and that was, in each case, an integral over the derivative, in quotes, is equal to the values of the original function only on the boundary. Now, there were people behind these great theorems, and there's a fellow named George Green and George Stokes. There is a third man who is also known as Lord Kelvin in addition to his given name, who played a large role in the dissemination of those two results, that is, Stokes' theorem and the Divergence theorem. And there are others who were involved too. And this, as a way of introduction, is showing you a photograph of a stained glass window at Cambridge in honor of George Green. So you see they have the region, they've sliced it up into these little rectangles to make the double integral there, and they show that the normal is pointing outside, which is telling you how you're going around the boundary as an oriented surface. And this is a stained glass window at Cambridge. Now, Green's theorem is named after the self-taught English scientist George Green. He worked full-time at his father's bakery from the age of 9 and taught himself mathematics from library books. He was a self-taught man. In 1828, he published privately an essay on the applications of mathematical analysis to the theory of electricity and magnetism. This contained basically Green's theorem, but it was not widely known at the time. He sent it mostly to friends. Finally, at age 40, he did enter Cambridge as an undergraduate, but died 4 years after his graduation. In 1846, Lord Kelvin found a copy of Green's essay, realized its significance, and had it reprinted. Green was the first person to try to formulate a mathematical theory of electricity and magnetism. His work was the basis for the subsequent electromagnetic theories of Lord Kelvin himself, Stokes, Rayleigh, and Maxwell. Now, Stokes' theorem is named after the Irish mathematical physicist Sir George Stokes. Stokes was a professor at Cambridge University. In fact, he held the same position as Newton, Lucasian professor of mathematics. The most recent professor of mathematics, the Lucasian professor of mathematics that I am aware of, was Stephen Hawking. I'm sure there's someone else now, but I don't know their name, and was especially noted for his studies of fluid flow and light. What we call Stokes' theorem was actually discovered by the Scottish physicist who was Lord Kelvin. And Stokes learned of this theorem in a letter from Lord Kelvin in 1850, and has subsequently asked his students to prove it on an examination at Cambridge University in 1854. We don't know if any of those students were able to do it or not. Lord Kelvin was an Irish-born mathematical physicist and engineer. He was born in Belfast. He was a professor of national philosophy, which included mathematics, at the University of Glasgow for 53 years. He did important work in mathematical analysis of electricity, and very much so in first and second laws of thermodynamics. In fact, the Kelvin temperature scale is named after him, and he was the first to calculate absolute zero. Now, the divergence theorem, which wasn't really mentioned yet, is sometimes called Gauss's theorem after the great German mathematician Carl Friedrich Gauss, who discovered this theorem during his investigation of electrostatics. There's actually some debate as to whether he studied it, discovered it, or actually it was discovered before by Lagrange, but he certainly was the first one to give a proof of it. And also there are Russians who feel that they also discovered it first. But anyway, this is the divergence theorem. Now, things don't stop there, though, because here's a statement of the divergence theorem, and here's a statement of Stokes' theorem, and these theorems are true for any vector field, but in particular, they're true for vector fields of electricity and magnetism, which is what Maxwell's equations are all about. Now, I'm not going to go through any derivations here because this is a 50,000-foot flyover. But you can use the divergence theorem on the first two of Maxwell's equations and integrate through a volume, and you can get a couple of these laws. And you use Stokes' theorem on Faraday's and Ampere's law on an open surface with a boundary to get the others. So you see you have integral forms of the laws. Notice the bold-face things are vector fields. But we have partial derivatives, integrals over surfaces, line integrals, and so on and so forth. And not only are there differential forms of this over here, but there are integral forms here. Now, I think, although you don't know what H, E, B, D, and J are, if you did, you would understand all of these theorems because we've talked about all this notation and what these symbols actually mean in this course. Now, Maxwell's work was very important because every electromagnetic form or radiation, visible light, X-rays, sunlight that heats the earth, radio waves, television waves, and Wi-Fi signals, Bluetooth signals, cell phone transmissions, and GPS all consist solely of electric and magnetic fields. And everything you need to know about how they propagate and interact with materials is completely determined in the above equations, which were unified and explained by James Clerk Maxwell in the 1860s. So this is the sole content of a course that you would take in your physics that's called electricity and magnetism. And this would be a core part of your curriculum if you were studying to be an electrical engineer. James Clerk Maxwell was a Scottish scientist in the field of mathematical physics, and his most notable achievement is those equations that I showed you on the previous page, 4 equations, a differential form and an integral form, which bring together for the first time electricity, magnetism, and light as different manifestations of the same phenomenon. Maxwell's equations for electromagnetism have been called the second great unification in physics, where the first had been realized by Isaac Newton. Now, there were subsequent unifications, and those are Einstein's field equations. I think I misspelled Einstein, sorry about that. But Einstein's field equations and great unifications are still being pursued when people talk about the theory of everything, and one of the contenders here is string theory. So you see, it never really ends. It just keeps going on and on and on. Theories and corrections to the theories, and mathematics always. In closing, please note that it is all math. And I believe it to be true. If you can do the math, you can do anything. Now more than ever, though, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless each and every one of you. Take care.